translation is she is at the work. So.
Yeah. Oh, okay.
I will just test
Yeah.
this.
Я ще того не зробила.
Що далі?
Не знаю, що тут треба.
Не, ну треба ті команди ввести, а я їх...
А то Ководівська віртуальна машина, чи GCL, чи Iraq?
Ну це GCL.
Ну, GCL це наша.
Просто я так не Вадима попросити, щоб... Там дуже просто, але...
Я просто ще не прийшла той блок.
Так, ні, зрозуміло. Я з того, що я тут проходив, але не настільки, щоб код писати. О, є.
Тренди.
No, it's...
Step 1.
Okay, I think it's just... Jim, we were testing this kind of, you can see it, it's kind of terminal, but it's not real virtual machine or simulator. I think it's just some script
Yeah.
to check if you type correctly the sequence of the letters. And all this was typed by me, but if I mistype any
Yeah.
letter, it just tell me that you are correct and
Yeah.
start from the... So I don't know, Vitaly was right, it's not a full terminal.
Mm-hmm. But it's sort of like a what they call a 3270
Yeah.
format.
It was fast that earlier.
Yeah.
It was,
So, like to use that Hercules computer, you have to get on with a 3270 emulator.
yeah.
So you had your
Я з симулятором не розібрався, тут Джем ще показали, які нюанси, я вам не розкажу, як це спіскати. Ну і наступний раз зустріч в себе. Ну, Джем скажеш, але ну, понеділку. Jim, so I will return.
okay,
in an hour.
okay, yeah.
Хоча не пані, як я 3 дні без ноги запишу.
Ти почав їти стільки чого.
So, the old Z system had a controller, I forgot the number of it, but it's like 32. Some kind of model number. And then there was a terminal, not quite a laptop, because all it was is a dumb terminal. And it was, so nowadays you have to get something like, so if you get onto a mainframe, you have to get some kind of 3270 terminal to log onto this guy. Makes sense? So what we were looking at before is a different type controller, like a 3290 type. So this is the mainframe sort of view of the world. So Z system, data communication lines, in this case, goes out to someone that understands the data communication protocol, controller, terminal. And nowadays you can put 3270 emulator software on your PC, so this guy looks like an old IBM terminal. They used to have disk controllers. Well, so there's some kind of number here. I don't remember. But you'd have a disk controller then would control a whole bunch of disk devices. And these disk devices are, nowadays, the IBM machine thinks it's talking to a disk device that has so the IBM machine nowadays thinks it has disk devices, disk drives. And the disk drives have this 3390 formatted drives and tracks, and the tracks are 56.64 bytes in length. And they're in this key count data format. And we talked about the format. The devices that you have are just fixed blocks, one after another. So the devices in your PC are blocks. These blocks used to be actually 512 bytes. And now 4K. So these blocks on your device each one is 4K in length. And physically, just
4K bytes.
for a block, yeah. Because, well, the way the track is laid out,
It's like a block.
4K. And then so no matter what records you're reading or writing on your PC, the disk drive of the PC is always picking up an integer number of 4K blocks. And then it's up to the access method to figure out, well, where's your record? If you have a 18,000 byte record, then you're going to need, you'll pick up 5 blocks at least. See where I left off that.
Рефлексии. Речистилец. Нет, это по команду работает. Речистилец гораздо. Значит. Передрадует команду. Что? Відрозву в этих смысле про команду. Что за смерть?
Курс.
I'll go back to the last discussion, that's where we had.
Ты уже была учить. Стоколу проходили за свій раз. Computer Science. Он спать не сподобався. Собака. Знаю, хоче хто закинув. Ну.
So what did you remember from last time?
Ascendant.
Assemble. We talked about base displacement addressing. Does that make sense?
Well, I think I will ask someone if someone wants to join us.
Yeah.
I will not do that.
Let's see. We talked about the cycle, what the steps an instruction has to go through. And we added to this discussion a little bit of pipelining. Pipelining allows more instructions to be executed per computer, several instructions to be executed every cycle of the computer. The pipelining works pretty well. However, if you do a lot of branching, it doesn't work too well. We talked about instruction format, and the format here, we're talking about the instruction statement in an assembly program, something that a human would write. The format was, you can have a label, name, you can have the opcode, in this case, compare logic characters, and then you have one or more operands. The operands are separated by commas, no spaces between those operands. When there is a space, it's treated like a comment. Column 72 is a big deal because if there's anything in column 72, the assembler thinks this is lots of writing and it's going to continue on to the next statement.
Good reason. Like Web 8 in Python.
Yeah. So we talked about instruction, again, same kind of format. We have the opcode, MVC, move character. The characters start. And the other thing we have to be aware of when we're coding assembler, which is different than coding in your higher level languages, Python or something like that. When you mention a variable name, it has more than one attribute. In your Python programs, it was a beginning location. When you have a variable name like y, it had what? A beginning location in memory, but it also had other attributes. It was a certain type, like character, or a number, where the number could be in several formats, floating point, binary number. It also associated, when you decode it in Python, the variable name had other attributes like not only the type, character and so forth, but also a length. In assembler, you have none of that. You have to remember what is Mrs. Y. Because all you know is this is the starting address. So it's a little more, you have to be a little more careful in assembler because you have to keep track of this by yourself. We talked about in IBM they use EBCDIC rather than ASCII. So EBCDIC is a coding. It's good to remember that Charlie 1 is a letter A, and the numbers start with F0. Okay, so that's 2 hex digits, F and 0. Okay, equivalent numbers. A little historic thing. Now, But some of the instructions it will write will turn into machine code. We'll make a statement and it'll actually turn into a machine instruction. They'll be in our program.
And how they are turning it?
I'm sorry?
How assembly is turning to the machine instructions?
That we're going to, I want to do that. Okay, so I'm going to have a lecture today. If I can get to it, you guys are doing pretty well, or at least you look like you are, because you're smiling and nodding. And if I can, what we're going to do is hand assemble. We're going to write a program in assembler language, and then we'll hand assemble it. We'll do what the assembler does. And it'll be all set to load into the machine. Okay?
Yeah.
And that's sort of like the skill we need. There's some instructions you write in assembler that do not turn into machine instruction. But they're instructions to whom? The assembler. Hey, do this. Define constant, define storage, define constant, do those. Define storage says just set up an area of memory this length. Now, in define constant, you're telling the assembler not only to set up this area of storage, but also to initialize this area of storage. So define constant, keep in mind this define constant, the constant name is a little different in other languages. In other languages, when you declare a constant, you cannot change it in the program. That's why you call it constant. An assembler, it just thinks this defined constant is only for you. You help you remember, but you can change any one of those bytes in the constant. You follow? So it's sort of a misnomer, misname. It's not really a constant, but you think it's a constant. The machine doesn't. When you do a defined constant, the maximum memory you could reserve is 256 bytes. If you do a defined storage, you can actually reserve up to 64K. There's various data types. This is, again, this is in the programmer's head. The machine, it doesn't matter, he just sees bytes. You guys are okay with these things, like CL3 means what? I'm defining a length of 3 characters, and I'm going to initialize it with an epsilon A, an epsilon B, and an epsilon number 3. Now that's not a value 3, it is the character 3.
How to define value?
We will show you how to do that later. We have several different formats to define values. We have binary, packed decimal, zone decimal, floating point. We'll be talking about each one of those a little bit. We'll also have to convert from each one of these numeric values. We'll convert between binary to packed decimal to decimal. Again, we're not going to do floating point.
One question, may I
Yeah.
go to store it and write something there?
Oh yeah, go ahead.
So then it would be the letter E.
The letter,
E. Right?
yeah,
May
yeah, we can erase.
it would be like, for example, 3, then C, 3 and then 8. Then it would be like 8, then nothing here, and then again 8.
No, what this will do, since this is a defined, first of all, you're gonna set up 3 bytes in storage.
And if here is the 3
Yeah.
before.
So you're good with this, you have 1, 2, 8. So you're setting up 3 bytes in storage.
Okay.
And you're initializing it. Instead of an 8, let's put the letter A.
Which letter?
A.
Okay.
The letter A. So the letter A in human, in the machine, it will turn that into an epsilon C1.
And this 3. What do we mean?
Now, okay, this is if I do.
Okay. And
So this will turn into this. Now, if I put let's put a 2 so we don't confuse it. Okay, just, I like your 3, but
okay.
just okay. So that'll create 2 groups of,
Okay. That was the question.
I understand.
good? Good question. Usually, usually like I write it. Whereas this represents the space character. Okay.
Okay.
It's just a matter of writing style. Because we saw before, you could have like this is valid, but the only thing that counts is CL3. These other guys, you just wouldn't be loading that D.
Mm-hmm.
Charlie 1, Charlie 2, Charlie 3. ABC and epsilon.
Mm-hmm.
Okay, so now, we're gonna learn this because we're gonna hand assemble a program. I'm not sure, like, as I said, I can get to that today, but definitely the next class we'll be doing this. And you notice every time we define something, we're setting up storage, so the location counter increments by the length of either the instruction or the storage that we're reserving. We can tell the assembler to give a place in. We could tell the assembler to give some of our names an alias, so to speak.
And then
2 names.
Then this name will be same size as F name,
No, it doesn't have a size.
but it's
See?
like the same address.
Name is the name of the 7th, this location.
Okay.
Name is also another, so you can, in your program, either you could write name or you could write F name. So this is only to help the program, and we'll see this.
Okay, and can we write some words or some letters in F name
Yes?
and in name?
Yes, but it wouldn't, no, yes, but it wouldn't make any sense. It would just confuse the next person.
Okay.
So let's try this. Instead of making 30 bytes, let's make this CL5, 3 and 2.
Okay, and why do you need zip name then?
Because in our program, sometimes I will want to refer to all 30 bytes. Sometimes I want to refer in the program only the first 10 of these 30 bytes.
Like very special comment to go.
Yeah, so it's more for humans when they're reading the program. This is not for the computer. The computer, all this does, this, 30 bytes are put in the computer. And whatever the programmer wants to call it, it's up to the programmer. Good? Okay, keep in mind, these names in assembler are the location of how many bytes? Always. You don't have type, when you eventually get your machine programmed, the machine does not know about types, it doesn't know, all it does is do exactly what you tell it. So this is for the programmer. Good?
Mm-hmm.
So, this is a common way to, if you're doing this in assembler, you're setting up a print line, where you're reading a record, let's say you're reading a record, and the record has 30 characters of name data. And sometimes you want to pick something out that's the first name, sometimes you want to pick something out that's the second name. And by using F name and L name, it just helps somebody who's reading the program what's going on. Another way to do this is with OR. We will be using OR a little later, okay? This guy likes to show this. He's building a report with OR. Interesting. Some people do this. Most, I don't know, programs I've seen used this method instead of this OR method. So now we have move character instruction. We're going to talk about that. Now here's what's difficult about assembler is you're writing one in assembler like MVC X comma Y. And then it's in one format, but the machine instruction will be in a different format. So let's take a look at that. Now here, our author of this overhead, MVC is a type SS1 instruction. So what you learn is not only the name of the instruction, you have to know the format of the instruction in assembler. So let's take a look at that. There's my reference card for 370. You guys are talking. I think it's, well, that's just, okay, here, 370 reference card. Okay, so here's our reference card we talked about last time. And if you're programming an assembler, you always have this around. It has our machine instruction. And the machine instruction we're talking about is an MVC, move character. So we're going to go down to move character. If you see it, let me know.
Yeah, up
The
previous page, yeah. MVC move, D2 SS.
somewhere around here.
Yeah.
Okay. Yeah, this is a move character. The opcode is D2.
Like to use this operation, we need to.
In other words, a machine instruction All the computers work the same way. There's a machine instruction. The first thing on the left-hand side of this machine, number of bytes. Well, first, how many bytes is in this machine instruction? It's, where is it? I'm sorry.
I could make it bigger.
Yeah, wait, I can do this here. Let me see. Okay, so it's a move instruction. What's being moved in this case are bytes. We presume they're characters. Do they have to be? No, it could be values. You're the assembler program. You can do whatever you want. The outcode, the first byte, is D2. Now, the first byte of every instruction is the outcode, like what to do. Because what's going on is the instruction address register is always pointing to the next instruction. So it starts off, here's the instruction we're going to execute. What is it? It's a D2. Oh, I know what a D2 is because it's a smart computer. It says D2 is a move character.
We can write D2 instead of MVC.
That when we act like assemblers, we can write the machine code. And that's what we're going to do later. But normally, we're going to write an assembler. The assembler format, now here's the trick. The assembler format is this. Well, I'm pointing to the wrong.
Yeah,
Yes.
yes.
Okay?
Len.
So this is what the format that you're going to write. But then it's going to get converted into an SS type instruction. So let's write down both of these, okay?
Like storage to storage.
Yeah, it's a storage to storage instruction.
And why first brand has Len and the other one?
So let's see it. Well, hand and assemble is one instruction, okay? So the format you're going to use, D1, LD1. Wait, D1, correct? I got that right? D2. D1,
Like one, okay.
L, it's got a comma.
Like it's two operands. Like, and why the first one has names and the other one don't?
Yeah, so this is the format. Now, when we're writing, now here's the trick, this is part of life of assembly. When we're writing assembler, we're writing it in a format that's expected that a human is reading it. Okay? So these numbers are human. When it gets converted, it's going to machine instruction. So we're going to then set up this machine instruction. We're going to convert what you write to the machine instruction. And then that's what the machine's going to be reading in the memory. So, no, I don't want 12. I'm just going to use it. I want to move, let's say, 4 bytes. The base register I'm using is register 12. It's a common register. In order to write this instead of just 12, EQ. So before I write this in my program, I put R12 equated to 12. So the assembler says, oh, R12, I don't know what that is. Oh, every time I write R12, just put in number 12. Because this is easier to read than if I just add 4, 12. It's very clearly that I intend to make this a register. So this is memory. For the purpose of doing this, memory goes from, in our memory, we're just interested in 0 through locations. What did I do? Yeah, 1, 0. This is an X. So
You're a human.
that's right. So let's say I have
Can you repeat again? Like,
good. So let's take a look at this.
We need to move.
I want to
forwards.
move whatever's here to here. I'm going to move 4 bytes. In our case, I'm going to make it simpler. There's another way to do this, but I'm just doing this. Because this could be a number up to 256. So I'm just moving 1 byte. From where? From this location to this location.
From 1 to.
I want to move the C3 to here.
Again.
I want to copy this
Mhm.
to this.
And in this one box can be from 1 to 256
Yeah.
because one
what-
box is
yeah.
like 1 byte. And 1 byte can contain
So this is how many bytes I want to move.
Okay.
Damn.
like the question was that you said that in one box can contain from 1 to 256 characters.
No, my instruction can
Okay.
move from 1 to 256 characters.
Okay.
Byte.
8 and 6. Okay.
Because that's what the instruction does. Like, I have some stuff you have to carry from here to there. And you can carry from 1 gram to 256 grams.
And why not more?
Because that's all the instruction holds. So, I'll show you that. Let's take a look at the SS type instruction.
In this
Good question, that's a good question.
What the default amount of which stack can hold? Like,
That, I'm gonna show you, just give me several seconds. So, this is a limitation of instructions. So what we're doing is look at the SS instruction format. You can look at it. I know you're whispering. Okay, so that's what the human's writing. Now let's see underneath what the computer is going to write in physical memory.
Okay.
So that's how SS instruction is set up. First of all, the format we're using is this. We have one length, base displacement address, and base displacement address. Okay, so this is an SS, sometimes they refer to this as SS1, SS2. Do we have somebody else online? So the first thing we have is, on any instruction is what? The opcode, 1 byte.
Okay.
And what's that going to be because it's MVC? Okay. Next in the instruction is the length followed by base and displacement. Okay, now, what's going to happen here, because we wrote this, okay, we're going to move 2 bytes. There's 2 nibbles for length, 2 hex digits. So 2 hex digits, since we're going to move 2, inside the instruction will be a 0, 1. Humans start counting from
1.
computers start counting from 0. So although it says 1 in the machine, it's already 2. And so this is like hex, these are hex digits. So this opcode is 2 hex digits. D1. This is really 2 hex digits, 0, 1. So the instruction only allows 2 nibbles, 2 hex digits for the length. So that means the largest value I can have in here is FF in hex, which equals a human 255. It wouldn't make any sense to issue an instruction that says don't move anything. So they designed this to move anywhere from 1 to 256 bytes. Did I answer your questions?
Yep.
You look like a non-believer. Okay. What's going to be in here? In both cases, I'm using what? R12 for the register. Fingers. A, B, C. Ah. So from Wait, do I get this right?
Not 8.
No. I want to
10. Yeah.
When you write, you're writing in, wait, I'm right, offset 16, which is 16, that's 10, I'm sorry. Three nibbles.
Mhm.
12 bits. There's 3/8 digits. Three nibbles.
Nipples.
Yeah, a byte is 8 bits, a nibble is
And 4?
4 bits.
It's like a half.
2 nibbles in a byte.
Like a half.
Yeah. So there's a lot of instructions. Pardon?
You said 4. There is 3.
Yeah. 1
Oh,
equals a human 4095. You could try it in your calculator if you don't believe.
Yeah.
So this becomes our sort of a problem, but this is kind of what I'm trying to get you guys used to a little bit. Just exposure to how these assemblers work. If you want a job in this kind of stuff, it's really interesting.
Yeah.
They're like solving, there's like solving, you know, you get those math problems, you know, like this happened, like, so how many, and sort of like solving math problems. The times I've used this is 1. Times I've used this assembler is actually the code stuff, changing the operating system. Usually they're very small routines. And rarely would I be doing things with characters. Usually I'm looking, you know, like doing bit manipulation, XORs, ORs, ANDs, that kind of thing. You have that in, good. So I'd be doing that kind of stuff when I'm ready. But other times I'm looking at this sort of stuff is if you're doing any reverse engineering.
Mm-hmm. Yeah, it's fun.
Yeah, have you done any of that?
Not yet, but I want to.
Okay, yeah, I may talk a little bit about reverse engineering, if you guys are interested. Just a little bit, just, my idea of this assembler isn't that you guys are gonna get out of here and do assembler, but I want you to have some idea like what is it, how you go about it, and very importantly, you should know the purposes of it. Like, why does somebody wanna do this?
It's the biggest purpose to use something.
Yeah, so one of them is sometimes you actually, now in the old days, so if you don't mind, I'll just kind of, let's just talk about assembler. In the old days, people actually wrote a lot of stuff in assembler. For one, the compilers weren't as good as they are now. And usually a human is always smarter than a computer. You know, like your, I've got one of these little, Adreno or what is it? The operating system on your phone. Yeah. It has like the intelligence of a worm. You know, it's not that bright.
It's an operation system.
Yeah, humans are always brighter than, smarter than computers. Maybe in the future it'll change, but right now it hasn't. So, in the old days, a human can write better code than the compiler could. Now the compilers have gotten better and better, and humans still sometimes can write better code, but it just takes too long. So there's always a trade-off between performance and humans. So sometimes our computers are fast enough to go, it's not worth 2 weeks of time just trying to speed something up. So in the old days, we used to actually worry about, you know, how many cycles a move character would take and things like that. So that's one reason is to actually write code. Not done too much now. The other thing, the second reason, that we'll see a little bit later, especially when we get the emulator going, is to find problems. A lot of times a problem, you'll end up just with a dump of your address space where your program is running. And you're trying to find out from that, like, what happened. So you wrote some code, but here's what the machine thought it's doing. So it's always good to, like, here's what the other person's thinking and actually performing instead of what you think is supposed to be going on. So it helps, knowing assembly helps debug things. The other reasons also, one is reverse engineering. So you have some code and you're trying to find out what did somebody write
To hack something.
to make that code. My experiences in that are a little bit, the first time I actually had to do something useful with it, I sent a programmer, I was working in Washington DC, I sent my programmer out, Mitzi, to Colorado. This is like 2/3 across the US. And she had this disk of routines that we purchased. And to use it, you had to enter a password. So she goes out to a customer in Denver, and that stupid disk didn't work on the customer's machine. So this is an expensive deal. You know, she goes out there, there's a plane trip, she rents a car, she's staying in a hotel. You know, like, can't do any work. So what I did is I went on the disk, figured out how it worked, and bypassed the password checking. So that was my first experience with that. You know, actually doing something useful, reversing.
Also to hack something, it's useful.
Yeah, now the other people that do reversing are people who are studying viruses. So if there's a virus, one thing you want to do is find out just what is it trying to accomplish. And the idea is to go through the program and try to understand what it's doing. If it's talking to a botnet, you want to find out where are these botnets, what are their names, either to go after that or to create a countermeasure. And this reverse engineering, to do that, you have to know, of course, the assembly.
It's better to be the guy who is writing viruses.
No, first, he's a bad person, usually, unless you're working for Ukraine, and you may want to be attacking as a countermeasure, somebody that's hacking Ukraine's like military system or government systems.
Not bad.
So it's very useful. So all these skills are good for good and for bad, whatever you want to do with them. You're in business, you're going to have to learn accounting, I gather. And one of the things you're going to spend a lot of time figuring out is just how do people cheat with accounting. It doesn't mean that the Catholic Uku's trying to teach you how to cheat in accounting, but you have to know, like, what are they doing, what should I be looking for? So to make countermeasures, you have to understand the bad people, what are they up to? There's another area of reverse engineering that's becoming fairly important. There's something called a write to fix or right to repair movement. Have you heard of these? So nowadays, here's a good example. Do you ever see these big machines on a farm? They're like harvesting the wheat, you know, or, they're kind of, and all of a sudden a big bale of something comes out. Okay, those things have a lot of computers in them. Like your car, a new car probably has about, I don't know, maybe 60 computers. The seatbelt every seatbelt has a computer, lots of computers, they're all networked. But on these large combines, the thing that harvests the wheat, they're all computer controlled. And the problem that people are having is that the only people that know how that works is either John Deere or Caterpillar or whoever makes the machine. And to take one of these big machines into the repair place, just moving it, maybe $1,000 back and forth. You know, it's a big machine, you gotta put on a truck. And there's an industry of people reversing those computers.
Not so fun. Not so fun.
You don't think that's fun?
Combines?
Well, you're worried about it. You guys are going to be doing something with arms or picks, things like that. I think next course.
Yeah.
Yeah, so you're doing the opposite. Where you're making the code. Somebody gets your machine, it's in a product. Somebody, whatever you're going to create, you make a product out of it, you sell it. Somebody gets it, and all of a sudden it's not working right. There may be a program bug in it, or it just stops working, and they want to understand how this works. How are they going to do that? They either have to contact you and you say, well, I'll do it, but it's going to cost you $1,000. And somebody says, I'll do it myself. But in order to understand what the chip's doing, they're going to have to reverse engineer your code. And I think that's a lot of fun. There's the other thing also along with that whole industry, there's a lot of measures, countermeasures. People write code in a way to make it difficult to reverse. And it's getting harder and harder for both sides. So it's
Boring.
I think it's very interesting, yes. Okay. So we went from something a human wrote to something that's in machine code. The difficulty is these formats, the order of the operands in the assembly statement is different than the order of operands in the machine instruction. There's also several ways of writing this. So let's see, first we changed 1. Instead of putting R12, I could originally just put in 12. To make it a little simpler to understand, I put in R12 is equated to an actual number. The assembler, every time it sees this, replaces this with a human 12, which puts in a Charlie in this particular operand, the base 1 operand. We can also have done this a little differently as well. So here's our, I'm just doing this. Here's our counter during the assembly process. Does this statement take up any room in the computer?
No.
No. It's just an instruction to the compiler. So as this assembles, this is relative location 0. Relative location 0. lost. I'm counting wrong. I'm good. What should this be?
Next one? 8? No,
Seven.
it's a 9.
No,
8
no,
or 8? 8. Okay. Ой, ще будуть загадки. Zero, 10.
So,
And now we use MVC.
yeah, so let's do this again. We're going to rewrite this instruction and have this assembler help us out.
2 field, comma, from field.
Yeah.
And when we reverse engineering, when we are making reverse engineering, we see only machine commands.
Yeah, you're going to see this, and you're going to have to convert to this, and maybe even, these names, you can make up your own names, do you understand? These names are not going to show up any place in your code you're reversing. Does this help, or? Learning taking place?
Yeah.
So, you have this card, and the card will show different types of instructions. The RX instruction up on top, opcode, and then 2 nibbles. So this guy is only, this instruction is, the RR is only 2 bytes long. So move the contents of one register into the contents of another register, for example. Or add the contents of one register to another register. RX is going to have 2 operands. The opcode, one operand is going to be the register. So in other words, the register is going to receive something. Where's the other operand? Well, you have to calculate 3 things now. The base register contents. One of the other registers will be an index register. And the third register will be the base register. So, oh wait, did I say that right? You're going to have base register contents, index register contents, plus a displacement. This is an interesting instruction in SI. This is a storage immediate. And what's going on here, now internally, it's going like this. I'm sorry. the assembler code is going to be going from right to left. But the instruction, this is going to specify an address. I'm sorry. This is going to specify an address in memory. How's it going to get the address? The contents of the base register, plus a displacement. It's going to be an address in memory. And there's going to be an immediate operand. So this byte, whatever the value is going to go into this place in memory. The immediate means it doesn't have to go out someplace else to get the value of the operand. It's already in the instruction. There's a type S. We'll be seeing examples of that, but it's just an opcode and one location in storage. And we talked about this guy. So again, this is, we call it a green card. It's not green anymore, but this is a lot easier to use than the principles of operation, which is a big, it's at least 1,000 or 1,200 pages nowadays. So this is a lot easier to use. And this shows you a couple things. It shows you the format of the instructions, the machine instructions, into the machine, and then it shows you how each instruction works. Again, the name of the instruction, sort of a description, the mnemonic, an assembler, this is what you'd use in an assembler. This is the opcode, the first byte of the instruction, the format of that instruction. How you guys doing? Good?
Yeah.
Okay, so we did MVC. Now here's what the assembler will do if, yeah, back here. The assembler will make assumptions sometimes, which may or may not be what you want to do. For example, if we wrote so I have three ways a human can write an assembler instruction. Okay. One way is to sort of specify all this stuff. This is closest between a human and what the machine is going to do. Or you could simplify it and you could explicitly say how many bytes you want to move. Or you can not say how many bytes you want to move. But if you do this, what it'll do is
All data from field?
no, it'll just take the length
No, yeah,
of
like
two fields. So two field, you did a defined storage two, and the assembler is going to say, since you didn't write it down, you must mean two.
the smallest one.
Yeah, no, not the smallest. See, that would work in some of the higher level languages, but your coding and assembly,
Okay.
you know what you're doing.
From first operand, len.
Yeah, it's gonna take the length of the first operand and use that. Good? So the problem is this. Well, I'm not, okay. Let me try a different color.
And if you don't say which register to use,
It's gonna use the base register, I'll show you that later. Later on, we're gonna have a using statement.
Namespace is TD.
I'll explain out what that is later. But you're gonna have a using statement up here, and it's gonna know to use R12 when you don't say anything about a base register.
could it be in some way better to use the second line of writing it? Like,
You're a human. If this helps you as a human, good. If it doesn't, it's gonna, no matter what, any one of these will turn into the exact same code for the machine.
like it will not be do it faster or something like that, just,
Since these all turn into the same machine code,
It's
okay,
already the fastest.
exactly the same thing.
okay.
How you code is only for you and the next person. But but when you're coding this stuff, usually you want to heavily comment in assembly. Because you come back the next day and I'm thinking, what was possibly in my mind yesterday?
Not only in assembly.
Yeah,
Mm-hmm.
but it's even more important, yeah, but it's very important in assembly. Assembly, I think, takes a lot more concentration than some of the other languages, the higher level languages.
Definitely.
Yeah, because you're kind of doing this and you're thinking, what's it up to? I write this and you're kind of in the back of your head, you're thinking this. At least that's, my.
I said that if I will start learning assembly, where in the big amount, I will smoke more.
You'll smoke more?
Yeah.
Oh, no, don't do that. I noticed, just a little side, I noticed that in Ukraine, people smoke a lot more, especially young people. I'm really surprised. My dad died of lung cancer,
What?
and yeah, you don't want to smoke. You
You
vape,
don't want
or you just actually have cigarettes that you light with a flame?
No. It's like it's like heat.
Vaping.
No.
It's like a third type of smoking.
When you heat the tobacco, not tobacco.
Oh, okay. Try not to do it. It's extremely addictive.
Yeah, I know.
My dad tried for decades to stop, and it never worked, and he just died. It's
We
not
were
fun.
yesterday visiting Oleg at his work, and he wasn't smoking for really long.
Uh-huh.
And it was just, I don't smoke, I don't smoke.
It's a huge addiction. It's more easier to get probably addicted to tobacco than cocaine.
Because cocaine.
Cocaine's worse for you, I'm not saying that. But as far as the addiction, it's very easy to get addicted to smoking cigarettes. It's up to you. But that's my comments. Okay. So, a lot of things happen, and that's what we're going to be doing. We're going to write a program, and we'll do that next time. We'll actually write a program, and we'll assemble it, hand assemble it. How you guys doing on this, okay?
Yeah, fine.
Yeah.
Okay. I don't want to go too slow. If I go too slow, you could say speed up, we got it already.
It's okay, like, well, okay, we will do it. I only need to learn the hexadecimal table.
Yeah.
It's like the hardest in this.
Yeah. So, what I'm gonna do here is, my goal is not to have you guys, so you can start coding all these programs. I want you to just be able to code a routine, understand how it works. Later in life, if you got time to relearn this,
We will
just a matter of memorizing the instructions,
Oleg will teach us a course of assembly.
Yeah. This will help you, also this will help you, I want to mention, if you learn this IBM assembly, it'll help you mainframe, it'll help you in all other assemblers. So if you need to reverse a PC program, you'll have a head start. It won't be that difficult to just get going on. So, we have move characters. Oh, that's what I wanted to show. Apologies. Two.
Sure, stop.
Okay, so from field is 1 byte in length. And so even though I wrote CD only,
One, the first.
okay. So what's going to happen? The computer will stop.
He will copy on the first one.
Yeah, because what it's going to do, it's going to move how many, it's going to try to move how many bytes if I do this. How many bytes will it try to move?
We will try to move 2, but then only.
Yeah, so it's going to go take this guy
But we have.
and move it here.
Yes.
Then it's going to take, oh, you don't own that space.
We'll also.
Somebody else owns it. So you get either a protection exception or some out of range exception.
Yeah.
Sometimes you actually own it. So I made it like, define something else here. And what you end up doing is whatever happens to be here, you copy it into here. This may or may not be what you want. This is why looking at dumps helps. Because you'll be able to see exactly what did happen. When you did your Python, right? Any other languages?
Python,
Just
C++.
a bit of C.
Huh?
It's
Python?
like, I know Python, C++.
Oh, okay.
And C#.
Okay,
Something
good.
else. Python.
Did you use an integrated programming environment when you did that?
Yeah.
Would you use
Integrated.
Eclipse or what do they use?
C-line. C-line.
Oh yeah, okay, good.
And,
Those integrated programming environments tells you a lot of what I'm going to show you now.
mhm. Sure.
So some of this stuff, I'm not going to spend, this guy has like 300 some slides.
403.
Yeah. So I'm going to go through a lot faster on some of them. The move character, we already got the idea. You move however many you say it'll move, it'll keep going to the from field, moving it into the to field. Good? Yeah, this guy didn't talk about something, nor the book talked about, something called, or just barely mentioned it. So I'm taking a little bit of a side to some hardware thing, okay? And there's something called microcode. So this has to do, what I'm referring to is this microcode, is when they're building a machine. You notice as time goes on in these machines, there's more and more instructions. Now, each one of these instructions has to be implemented somehow in the hardware. Now, the hardware, one way to implement this is to have a lot of little chips, and you go move, and all of a sudden, boom, boom, everything moves all at once. But I don't have enough money for that expensive of a machine. that does all that stuff all at once. But if I want the architecture, I still need an instruction called move character to move. So what can the manufacturer do? They could be sneaky. You get two instructions. One character instruction, or you can get a move character instruction, which will move up to 256. So here's what they do. The move one character instruction they implement. And then, if somebody tells the machine, do a D2, it goes to this little program called microcode. And what does that do? It does the move one character 2 times. So some instructions are hardware implemented, some of them are implemented in microcode. Now the microcode you don't get access to, that's the manufacturer did that, and that's all part of the wiring. So expensive machines have less microcode. I wanted to mention the microcode thing. Okay, so this guy's showing how this all happens. You don't need to know this. You get the idea, right?
Yeah.
Okay, so he's got a lot of examples, including he has one, you could go over this yourself, but he has one where he goes out of range. They have some tricks that this could actually overlap. So let me show you this. So what's this going to do? It's going to move from 2 field plus 1 to 2 field. So basically, I can overlap these 2 areas. So it's a way to fill in something with a constant.
Like to make it bigger.
No, just like if I want to, let's say I want a zero, let's say I want a bunch of spaces in a line.
So you like.
Yeah. So I initialize this, let me make sure I got this right.
But for what we need it, like.
Well, before you print out a line, you want to make sure it's full of spaces. So you're going to fill something up with spaces, you can fill up an area of memory with all somethings, like zeros or a particular, your favorite character.
Why is 5 there?
I'm sorry?
Why is 5 there?
We want to move 5 bytes.
Yeah, so I just, yeah, let's not moving 5 bytes. Oh, yeah.
Like whatever we are moving. There's a machine.
The standard width of printers used to be 132. Actually 133 because you have a little one character as a control character for single space, double space. Good?
Yeah.
You know, this is getting old, it's no fun because I can't see. Ah, I saw him up there. So we've got, okay, so this is an example of blanking out a line. So here's another way to express the length. Like L prime buffer is the length of the buffer. Buffer is defined up above as 133. You see? Blank on the line goes, they have all the courses in assembly, for some reason they want to blank out a line. You'll probably never use any of these in assembly. Rarely are you going to code something that's like printing things in assembly. You're using assembler, usually, like I said, you're usually doing bit fiddling, something like that. And if you have to write a report, then you just call it like a COBOL or PL1 or another language to write the report. You would not be coding it. This is real. There's some instructions that set the condition code. So part of the program status word on the extreme right is the instruction address register. Points to the next instruction. Part of that instruction address register are some condition codes. Now these are 2 bits, so there's 4 possibilities, and they will be set by some instructions. Always the arithmetic instruction. When you execute an arithmetic instruction, like add, subtract, it sets the condition code. Is the results 0, plus, minus, something wrong?
Mm-hmm.
So then some instructions have only one purpose in life. Look at the condition code. Is that a dull life? So what are some of these instructions? Branch equal, branch low, high, not equal,
No.
da. You get the idea, right? Okay, so some of these, now how do these branching instructions work? They're actually modifying, when you, normally a computer does what? When it's executing this instruction, the instruction address register is already pointing to the next instruction, right? So normally instructions go one after another. But what if you want to branch? If equal, go do something else. So branch equal is going to, if it's equal, branch equal is going to look at the condition code register, which is just a couple bits. If it is equal, it's going to branch to this address. And this address will be so, if it's this, if it's equal, what's going to happen?
End of the program.
I don't know what branch equal is in hex, but this to routine is going to be replaced with the base and displacement.
Okay, and why you wrote there to ADF and then to RTN?
Here, branch equal, this is what you're going to write.
Yes.
Okay, so you're going to have some arithmetic instruction earlier,
Like if
or let's say, no, sorry. Branch of 0.
yes.
So you do some an arithmetic instruction or you decrement a counter, you're implementing a loop. And then finally, okay, now it's empty. So what are you going to do? If the last result of the decrementing ends up 0, then the next instruction will not be the next instruction after, I'm sorry, it won't be the next instruction after the branch 0, it'll be someplace else.
Like go to.
This is go to, yeah. And how does the go to work? The address that's calculated with this, it's going to take what's in the base register, add this displacement, and where's it going to put this contents?
In another branch.
Where?
Can you repeat one more time, please?
Okay, it's going to, this to routine
To routine, yes.
is going to be base displacement. To routine is only in the programmer's mind. It's going to be in an instruction in base displacement format. So to routine is going to get calculated, the contents of this register, plus whatever value is this, it calculates that, adds those two together, and then does what with that sum?
Like found this operation and like with this block operation. Initial.
Instruction. It takes that value and puts it into the instruction value, into the instruction address register. Does that make sense? Are you just being agreeable, or you're actually?
No, this is the
Okay. Good? So, a branch instruction may modify the instruction address register.
Okay.
So then the next instruction is not the next one in sequence. It's either later or earlier. So there's things you could compare, a single character, a bunch of them. These are a format for the compare. How are we doing? I'm not keeping track of time. How are we doing? Good.
already like.
Hmm?
I think we can end and land in on
Break
Wednesday.
point now?
Yeah.
Oh,
And then on Wednesday start.
Okay. I'm gonna miss Monday. It's Labor Day in the US. So,
Congratulations.
yeah, and I'll tell you a little story about that. So when we come back, we'll actually give you an idea how this works. But also I'll have something I'll prepare for you to hand assemble a program. So I'll give you something somebody writes in human, and then you'll write that. Before I do that, also programs start with sort of a start routine and end with an end routine. So there's a standard start, a standard end, and then there's stuff you write in between. I need to show you how the standard start works and how the standard end works. So this is our linking protocol. Real quickly, I'll just tell you what that's going to be about, and I'm going to explain how it works. The overall problem we're trying to solve is this. it's typical for us to have one program calling another program. So we start off here. So this could be the so we have an input routine. We're going to get some input from the keyboard. We're going to edit it. Is that appropriate? Is correct? And then we're going to update some database. Each one of these, we're doing modular programming, so each one calls another one.
Mm-hmm.
So what happens in our case is bad day at the office for our routine number 3. Routine number 3 crashes. So we need to debug it.
And we go backwards and backwards.
Yeah, so first of all, we know that where the crash occurred in 3,
If we don't find it.
but that's not the problem. The problem is
Yeah.
maybe bad input.
No, first of all, we're searching for the problem in the routine. If the routine doesn't have the handling of it, we go backwards to the
Yes.
routine 2. If again doing the same and then backwards,
Exactly.
and then doing the base example, like
Good.
base handling.
Yeah, good. Now, in order to do this, we need to understand when this guy calls this guy, what's getting chained together? How are these guys, how do we know? There could be hundreds of routines in memory.
Mhm.
Why do we know we're going to go from routine 3 into 2 instead of one of the other ones? So that's where we're going to learn how this linkage works. So we'll do that. Yeah, that'll be good.
Okay.
We'll hand assemble a program. Well, first we're going to learn a few more of these. We'll hand assemble a program.
Mhm.
We'll learn how this linkage you can trace back. And then we'll do some file stuff. I'm not sure we're going to do all that next time. But okay, and we'll get together on Wednesday.
Yeah.
Maybe do it later on Wednesday because we are having a course.
You have to?
We're having a course of teamwork or something.
Oh.
So, in
Який
Wednesday,
час вона підійшла?
Та пізніше просто. У нас
Годину везіть.
і п'ятий до п'ятого.
Я б
вчора 4.
Тому що у нас готують.
17:00 would be okay in Wednesday.
Instead of Wednesday?
Yeah, 5 p.m.
In Wednesday, but it's
Oh,
fine.
well, just later.
Yeah.
Oh, I could do that, yeah. That'll solve a lot of problems. Okay? Good. Okay. How's this going for you guys? Good?
Yeah.
Are you learning or?
Yeah.
Yeah.
Interesting.
I've taught assembler dozens and dozens of times. This is the first time to university students. Interesting. You guys are doing well though, better than my other classes.
Everyone saying this.
So you guys are doing very well.
You were complaining that our teacher says that every other is worse than previous.
Better.
Better.
No. See, I'm used to teaching people who've been working in the business for a while, and they never learned assembly. And their boss thinks either they're going to assign them another job, or they think you need somebody that'll debug faster. And they send them to class for a week. And that gives me 40 hours of both teaching and labs to get them going. And you guys are going at a much faster pace than I would teach some of these guys.
That's cool.
So very good. But if I could make this easier or something like that, but I want you guys to actually code something. So,
Yeah, we want to code too.
yeah, I'm either with that IBM machine or with that emulator, That'd be good.
I'll write the instructions for students how to install it, whatever.
Yeah.
It looks like it works. We have
Okay,
tested it.
thank you.
Don't expect something fancy, but it's much more understandable than the trial of this.
Yeah. And they've done even in the Z390, they're doing access through file access. They're doing a lot of stuff, so if that works, we're in good shape. Good.
And regarding this, you should already know about code conventions.
I know it. So
let's-
that's why I just,
Yeah.
I started to.
Oh, and one other thing I'm gonna talk about is what's missing in this IBM. No stack instructions in the IBM architecture. So somewhere along the line, we'll talk about that, because this will be necessary to understand this, to do this in most other architectures.
Good that I know it.
Good? Okay, thank you.
Thanks.
Thank you very much, good, thanks. Oh. We'll have a coffee or something. How's this, okay, what we're doing?
Oh, perfect, yeah. It's a really nice.
Okay. I'm usually more
Jeff, if they do not ensure, they just put comments.
Oh, okay, yeah.
They,
But they keep coming back is a good sign.
yeah. I must go
Oh,
for meeting.
okay, so let me get out of here.